The 8 p.m. meeting today? Yeah. 8 p.m. Meeting. Yeah, I'm not hyped for that. You're not hyped? Yo. I got like next month. Jahan is not real. I gotta talk to him.
All right.
He just looked at me and then he said,
let's even get through some of the notes. 5.1. Sorry, it says 3.1. Okay, and then we'll use the second half of class to continue reviewing for your quiz. Again, I moved the quiz to Tuesday. We'll do 5.1 today, quiz review. Monday, we'll do 5.2 quiz review, and then your quiz is Tuesday. You'll get to use your calculator. I have some help sessions, but Friday is going to be, well, yeah, today, so this afternoon, and then Monday, 7:30 in the morning, and then Tuesday, I'll do a 7:15 in the morning. So. Yeah, AM, sorry. All right, so. Extrema. Extrema is just plural for maximums and minimums. So it just represents basically the highest and lowest points on the graph. Just some definition here. We have a relative maximum or relative minimum just means a hill or a valley of the graph. Okay, that's all it means. So we call it a relative. Well, sometimes you're going to see that word local, but typically we use the word relative. Typically we use relative instead of local. But relative, the reason why we use relative max is because relative to the points directly next to it, it's higher than those points. So we say that is a relative maximum. So here we call this a relative minimum because if I pick points directly to the left and to the right of it, it's lower than those points. So relative minimum. Okay. This point here is a relative max because it's a peak of it's a hill of the graph, but we also call this an absolute maximum because this point, there's no other point on this curve that is higher than that point there. So this falls into two categories. It's relative, it's higher than the relative points around it, but it's also higher than all the points throughout the entire course of the graph. So now sometimes some graphs don't have absolute maximums. For instance, if I have a graph that looks like this, there is no absolute max because we consider negative and positive infinity are not real numbers. So here there would be relative max and mins, but there would be no absolute max or absolute min because the graph goes towards positive infinity as well as goes down towards negative infinity. Okay, closed interval. So on the closed interval, so this is where my endpoints are defined. And for this, we can say that there is a relative minimum. We see a valley of this graph. This is also considered an absolute minimum because it is the lowest point over the entirety of the graph. Now this is the absolute maximum because it's the physical highest point on the graph. But there is no relative maximum here because we don't have anything to compare with on the other side. So it's got to be a hill of the graph. So an endpoint cannot be a relative maximum or relative minimum. Okay? It can be an absolute maximum, but not a relative max, relative min. It needs to have something on the other side to compare with. So basically a hill of the graph is a relative max, a valley of the graph is a relative min. Okay. Okay, this one here, this graph, this is an open interval. There's still a relative minimum and absolute minimum, but there is no absolute maximum. There's a hole here. I cannot pinpoint a singular highest point on this graph, because if I choose a point really, really close to that hole, I can always choose a point even closer, right? So I can never get to a specific number. So there is no absolute maximum value I can pinpoint if there's a hole at that highest point. Okay, so this is what we're going to work on today. It's called Extreme Value Theorem. I'm going to abbreviate it as EVT. So Extreme Value Theorem says if a function is continuous on a closed interval, then it has both an absolute minimum and an absolute maximum on that interval. Okay. So if I have a graph that looks like this, right, there's guaranteed to be an absolute max and absolute minimum. Now, there's kind of an exception to this, and that is if I have a horizontal line, then there's only one y value this entire graph. So this y value is considered both the absolute max and the absolute min. It's just all one value. But typically, we're talking about curves. So if I have, so let me kind of go through the rest of this theorem, which is related to extreme value theorem. If a function is continuous on a closed interval, so that means if there are no breaks along my graph, then my absolute extrema, or my highest point, has to be either coming from a critical point or an endpoint. Okay? Those are the only candidates that could potentially be a highest or lowest point on my graph. So how do I find critical values? Critical points is going to be where the slope of the graph is going to be 0, or your slope is going to be undefined. So in other words, is where your derivative is 0 or your derivative is undefined. So let me give you an example of a graph that kind of demonstrates that. All right, so here I have 4 candidates. I have 2 endpoints, and I have a critical point. This is where slope is 0, and this is where slope is undefined. So slope 0 and slope undefined, as well as endpoints, are all candidates for potential highest or lowest points on the graph. So what we need to do is we need to identify these points on the graph, and then we're going to test them, put them all into the original function, and see which one produces the highest or lowest y value. But we're doing this without the use of a graph. I just want to kind of show you that if this is what the graph looks like, these are the only candidates that we have to consider: endpoints and critical points. Okay, so let's go to the next page. So here are the extreme value theorem steps. First thing we want to do is we always want to confirm that our function is continuous on the closed interval. We did that with IVT, intermediate value theorem. So basically, any theorem that we're going to involve from now on, there's always that first condition: confirm that your function is continuous on the closed interval. It doesn't mean the graph has to be continuous throughout the entire graph. It just needs to be protected, and there can't be any disruptions on that interval. So if there happens to be a vertical asymptote or hole, we just want to make sure that it doesn't conflict with the interval. But if the hole or asymptote is outside the interval, then we're okay. Right? But we always have to make sure we state that as our starting point. And then obviously, if my function is not continuous on the closed interval, then I'll stop. There's no need to continue on with extreme value theorem, because if I can't get that first condition to pass, then I can't guarantee a max or a min, especially if I'm not able to see the graph. Okay, so we're going to first confirm our function is continuous on closed interval. Then we're going to find critical points. We're always going to find f prime. Then we'll set f prime equal to 0. And if there's a denominator, we'll also set the denominator of f prime equal to 0. And then once we confirm that our critical points and endpoints are valid, then we're going to insert them back into the original function and then compare the y values. Highest y value will be your absolute max. Lowest y value will be your absolute min. Okay, so let me show you some examples, and you guys can, so we can kind of see how the process looks. So first, we have a function, 3x to the fourth minus 4x cubed on the interval from 0 to 2. Now, do we have any issues with continuity with this function? Okay, thanks, Hannah. No issues, right? Polynomial, so there's no holes, there's no breaks. We know a function is continuous everywhere, but we still have to make the claim and that our function is continuous on the closed interval. I know it's continuous everywhere, but really we're only concerned about the interval, so we just have to make sure we state that as our first step. Okay. So we're looking for the highest lowest points across this interval here. So we only care about the endpoints, and if there's a critical point, the critical point has to live between the endpoints. Okay, let's look for the critical point and see if we can find a valid one between 0 and 2. All right, so let's find f prime. Okay, we go through power rule. What do we get here? All right, so here, there's no denominator. So there's no denominator. There's no need to worry about finding any critical points in the denominator. We just have to set f prime equal to 0 and see if we can find any valid critical points that could be a candidate for a peak or a highest max or min. Okay, GCF. I have two x values I can find. 12x squared equals 0 and x minus 1 equal to 0. So I have x equals 0 and x equals 1. Now I'm already going to test 0 and 2. So 0 is a duplicate. We're already going to test that, so no need to worry about it. Is 1 going to be a valid critical point? Yes, because it sits between the endpoints. Now, if there's a critical point that lands outside the interval, then we don't care about it. It's not part of our problem. And so now we're just inserting these points into these x values into the original function because we want to just know what their y values are. So 0 in for x, 0 minus 0, which is 0. Plug 1 in for x, negative 1. Plug 2 in for x. Time 48 minus 32.
Wait, why do you plug 2 in?
Because 2 is an endpoint.
Okay.
We always test endpoints and any valid critical point. Now, it's possible that we may have no critical points, and that's okay, because we're guaranteed to always have to be able to test 2 endpoints. There may or may not be any critical points, depending on if there's any that lands in between.
So if the derivative is a constant, there's no critical points.
That's right. So if there is a constant, then it's just a line. So there's no critical points, just the endpoints that we have to be concerned with. Okay, so f of 2 equals 16. Okay, so we compare the y values here. What's the highest y value that we see? 16. What's the lowest y value? Negative 1. Okay. Now, on the AP exam, typically when they ask for absolute max, absolute min, they're asking for the y values. Okay. A lot of times they would say, what is the absolute maximum value? And that word value means y value. Okay. So to help us, to help remind ourselves that it's really the y value that we're after, I want us to write it this way. I want us to write that our absolute maximum value is 16. Okay. And then if you want to include the x, you can say at x equals 2. But the more important number is that 16. Some textbooks allows ordered pair and say absolute max value is 2 comma 16. But because AP exam, they prefer, or they're always talking about the value, I'm going to stress that it's the y value that we're after. Okay? It's not the ordered pair. It's like saying what's the maximum height, right? If you say what's the maximum height, you wouldn't give the time. You would give that, that in feet, right? You wouldn't say at 2 seconds it's 16, right? You would just say 16. right? And then absolute minimum is what? Is -1, and then at x equals 1. This is not as important. If you leave this, if you leave the at x equals 2 or x equal 1 out, that's fine. I'm after the y values. All right, example 2. Now, obviously, if we could see the graph in front of us, we really don't need extreme value theorem. We can kind of just look at the graph and say, okay, that's the highest point, that's the lowest point. But we're using this theorem to help us gather information without the use of a graph. Okay. All right, our function is x minus 1 to the 2/3. Let's see, is there any issue between a -1 and 0? Normally, there may be issues if it was that root was a even root, but this is an odd root, so any negative number is not going to cause any issue. Our function is continuous on the closed interval, so we're safe there. Okay, so we have endpoints that we're going to be testing. Well, we also need to find critical points from the derivative. So if I want to find f prime, what rule do we have to involve here? Chain rule. Okay, even though there's not a whole lot with that inside function, technically it is still chain rule. So f prime, we do the outside derivative. Multiply by the inside derivative. So nothing is really going to come out that we have to keep track of from that inside function. So let's clean this up. F prime. I want to look at this without that negative exponent, so I'll put that x minus 1 below. Now, we know that critical points can come from both the numerator and the denominator, so it's nice to have it all under one fraction, because I can just look in both places separately. Is there any critical point from the numerator? No. If I set 2 equal to 0, that doesn't make sense, right? There's no variable in one of the regions, then there's no critical point. If I set the denominator equal to 0, is there a critical point there?
Yes.
Yes. Okay, so let's do that. 3 times x minus 1. If you already know what it is, you don't have to go through all these steps here, but divide by 3, cube both sides. All right, so basically this is a sharp turn of the graph. It's okay, we still want to use that as a potential candidate, because even though the function is a sharp turn, it's not a smooth point, but it is a potential peak or valley, right? Because we know that a sharp turn in the graph can still turn out to be an absolute maximum or an absolute minimum. But is +1, is this a valid critical point? Okay, what's the issue here? Yeah, so we always care about the interval, right? That is the boundaries of our problem. If something lands outside, it could be a critical point if the interval was a little bit wider, but here it doesn't. It's not part of the interval, but it's okay. Sometimes we may have a problem with just the endpoints to test. So don't feel like something is wrong if there's no critical point. You're just, with EVT, you're guaranteed that you're always testing 2 points. You may or may not have more than that. Okay, so they all get inserted back into the original function. And we just check their y value. So -1 minus 1 is -2. I square that, I get so it's the cube root of 4. That's just some positive number. Okay, if I plug 0 in for x, if I square the -1, I get 1. Cube root of 1 is still 1. So this is higher than this. So absolute max is cube root of 4. Absolute minimum value is 1. Okay, example 3. We consider, is there any issue here between 0 and 3? If I plug in 0, there's no issue. If I plug in 3, there's no issue. There's no, just have to worry about, is there something that's going to cause this to be a negative? I can't have a negative value under the square root, but I don't have any issues anywhere between 0 and 3, and the endpoints are safe. So our function is continuous on the closed interval. All right, I need to find the derivative. From the derivative, I can find my critical points. What do we have to go through here if I want to find the derivative?
Product and chain.
Product and chain. Yeah, product, because the x and the square root are outside of each other. And then chain, because imagine that there's going to be an inside portion we got to keep track of. Okay, good. Okay, so just want to kind of clarify what I did there. The outside portion was the parentheses to the 1/2. The inside portion was the 3 minus x. I'm taking turns with each derivative. Parentheses to the 1/2 is 1/2 parentheses to the negative 1/2. 3 minus x derivative is -1. And so it's a lot easier for us to find critical points if we can kind of clean this up a little bit. So I'm going to try to find a way to merge it into the same fraction. If I don't have common denominators, I want to go ahead and find that. So, but let me see if I can. Get this to at least show me 2 separate fractions so I can clearly see what my denominators are. The negative, I'm pulling that out in front. The 4 and 2, I'm reducing to be 2 over 3. I'm pushing this exponent, negative exponent back down. So I'm trying to do a couple of steps here all at once. All right, so I would like to get all this into one fraction so I can clearly kind of set my numerator and denominator equal to 0 separately and look for my critical points. What's my common denominator here? Good. I need something that's large enough for both of these to go into, and this is enough of a denominator for both to work. So I'm gonna create my common denominator here. Okay, balance each fraction. There's a change. There's a difference here. This old denominator is missing that square root. So I'm going to multiply the numerator by 3 minus x to the 1/2. And when I do that, the nice thing is this is square root times square root. So the square root drops out. I'm just left with 3 minus x. So it's just 4 times 3 minus x up top. This one has no changes, so I can just take the numerator as it is. So if I try to combine this together, distribute the 4 through, I get 12 minus 4x minus 2x. So that gives me 12 minus 6x. So here's my cleaned up derivative, so I can clearly see my numerator and denominator. All right, so this is where I'm going to be pulling my critical points. I'm going to look for slope 0. I'm also going to look for slope undefined and see if any of those will produce any new critical points for me to include for my candidates. So if I set the numerator equal to 0, what do I get?
2.
Okay. If I set the denominator equal to 0, I get divide by 3, square both sides, solve for x equals 3. Now 3 is already on my list, so it's not a new number we got to worry about.
It's
right?
inclusive, right?
I'm sorry?
It's inclusive.
It's inclusive, right? So we always test endpoints, right? So if there's a critical point that is an endpoint, then that's already a number we're going to test. All right, so we have 3 numbers to test. We're going to test f of 0, f of 2, and f of 3. They all get inserted back into the original function. So 0 would just give me 0. 3 would just give me, well, 3 minus 3 is 0, so that's going to wipe the whole thing to be 0. But 2n, I get 4/3 times 2 times 3 minus, well, 3 minus 2 is 1, so that just becomes 1. And then 4 times 2 is 8, so 8/3. Okay. And we really only care about the y value, so if there's a duplicate tie with my minimum, then that's my minimum value, right? So my absolute max is 8/3. My absolute min is 0. Okay, so that's basically it with extreme value theorem. We obviously want to get more practice into this, but really you're finding the derivative to find critical points. So whatever method is required to get to the derivative, you find that derivative, clean up if necessary, set the numerator equal to 0, set the denominator equal to 0. If there's no denominator, then that's fine. Just set the derivative equal to 0. And then make sure that whatever critical points you find, that you only use the ones that sit between the endpoints. If nothing sits between the endpoints, that's fine. That just means you only have 2 points to test. But you're always testing 2 endpoints and any critical points that are valid that sit between the endpoints. And we also want to make sure that we always make the statement confirm that there is no continuity issue before you move on to the rest of the theorem. Okay, so let's go back to our quiz review sheets and continue working on those. Okay, third page. Okay, function f of x is concave. Sorry, that's not meant to be a question mark there. Okay, the function is concave up at x equals pi over 6. Okay, not a question mark. What is the estimate for f of 0.5 using local linear approximation for the function at x equals pi over 6? Okay, so here are the steps for linear approximation. The first thing is don't look at the decimal. Decimal is not going to play a role until after you've built your tangent line equations. So whatever x value they give you, that's the x value you want to use. So go ahead and find your points. Plug pi over 6 into the original function, get that y value. And then next, find the derivative so they can use that pi over 6 to find the slope. Build your point slope form, build your tangent line equation, and then once you have your tangent line equation in front of you, then you can worry about that decimal. So first things first here, I just want to get my ordered pair out of the way before I look at my derivative. Pi over 6 and for x. Sine of pi over 6, think about your unit circle values. That's just 1/2. 1/2 squared is 1/4. Okay, next up, find your derivative. Derivative, we have to involve what rule here? Chain rule, yeah, outside, inside, yeah. Please repeat. Okay, from here we can find the slope. We have our ordered pair, we have our slope, build your tangent line equation. So I feel like some students get thrown off by the decimal. So don't look at that decimal until the very end, right? Get your tangent line equation up and running before you do anything with that decimal. Sine of pi over 6 is 1/2. Cosine of pi over 6 is √3/2. My slope is negative √3/2. Point slope form. What I like to do is I like to get that y by itself so that I can just plug in that decimal and enter all this in the calculator and it just gets that decimal value that I'm looking for.
Also, the answer is gonna be an like not, I mean, it is an approximation, but like rounded answer. Or like,
Yeah, you can, if it's decimal value, you can just give it to me in 3 decimal places. Yeah, rounded, yeah, you can use your calculator. Now, if it was non-calculator section on AP exam, you can leave your answer in this form and this will be perfectly acceptable. You're not expected to clean anything up on the AP exam, as long as you have something that is equivalent to a reduced version, you'll still earn full credit. But what you cannot do is you cannot leave your final answer as cosine pi over 6, sine pi over 6. You have to resolve these to get it down to a ratio value. You can't have any sine and cosine in your final answer. All right, part B, is this approximation an overestimate or an underestimate? Okay, because concave up, yeah. So if the graph is concave up, you can kind of, so concave up just means a graph that is U-shaped. concave down would be a graph where like N shaped or upside down view. And no matter where you draw your tangent line, it's always going to sit below the curve, right? Right, number 8, a cylinder with diameter of 2 feet contains collected rainwater. Water drains through a valve at the bottom of the barrel. And we know we're dealing with a cylinder, so we have to just remind ourselves cylinder is easier than cones. There's no need to do similar triangles. Get that radius to be replaced with a number, and then the volume equation will be a lot easier to work with, right? Don't hold on to that radius variable. There's no need to. So part A says find the rate of change of the volume of water. So we're trying to find dV dt, but first see what you can do to get your volume equation without the radius in there. Diameter is 2 feet, so what does that tell you? Radius is 1. Yeah. So your equation, before you find the derivative, is as simplified, as easy as just v equals pi h. So now we find our derivative. V becomes, yeah, dv dt, right? And then pi h becomes pi dh dt. Right? We're looking for dv dt, but we have something that represents dh dt. They give us something to use, so we'll put the expression that they have for us for dh dt and see if we can use that to continue working our way down to a numeric value. So they say that dh dt is negative 1/10 root h. We'll put that in for dh dt, and then we know what h is as well. At that moment in time, h is 4, so we insert that in as well. Okay, what's our unit of measure going to be?
Feet cubed.
Yeah, so think about volume, think about time. Volume is cubic feet. Your time is seconds, so cubic feet per second. Part B says when the height of the water is 3 feet, the rate of change of height with respect to time, is it increasing or decreasing? Now, if we see the fact that it's not talking about just rate of change of height, it's the rate of change of height increasing or decreasing. So rate of change of height is dh dt, then increase decrease would put it to the what? Second derivative. So we'll start with dh dt, and then we'll find the derivative of that dh dt. So dh dt is negative 1/10 root h. If I want to get that a little bit easier for me to go through power rule, I'll write it as h to the 1/2. So we know dh dt will become d2h over dh dt2, and then we just have to find the derivative here. And remember, we're still under related rates here, so we're going to find the derivative here and then attach a dh dt. So power rule, bring down the 1/2, subtract 1 from the exponent. We're taking h's derivative, so another dh dt will pop up. We know the representation for dh dt, so we'll put the dh dt representation in place of it. And then we'll clean everything up, replace 3 in for H, and see what that number gives us. But in this case, I think it's nice that, okay, if we replace dH/dt with -1/10 root H, which is here. Well, I cleaned this up first. I made it -1/20. I brought the H down to the denominator, made a square root, and then we know dH/dt itself is -1/10 square root of H. I see the numerator denominator root H goes away. That cancels out. I'm just left with positive 1/200. And this is a constant and it's positive. So we know that the rate of change is always increasing because my second derivative is always positive. Okay, we will do, yeah, you guys have homework over 5.1. I'll check that homework Monday. We'll do 5.2, and then we'll also finish up the rest of the review sheet on the last page. All right, come get your phones.
I think she's 19 again because somebody did like you were. No,